All right, lads and ladies, welcome back to Calc 1. Calc 1 Honors, no less. Today is an exciting day. We're going to introduce a piece of notation that no doubt you have seen in different places, but maybe didn't know what it was. And just like the derivative is hugely important, the thing we're introducing today is hugely important. In fact, it's so important that if you pick up a calc book and you open it to a random page, odds are you're going to see lots of these symbols on that page. It will be the dominant object that we play with for the remainder of the semester, and it will also be the dominant object that you play with in the first half of Calc 2. So today we are beginning our foray into the second half of kind of calculus's two halves. There is the differential calculus, which is what we've played with so far, everything to do with derivatives. And then there's this other thing called integral calculus, and that's what we're going to officially introduce today, is the integral. So Katie was originally going to lecture today, but we decided that it makes a little bit more sense to reorder the subject matter a bit, even though her section is section 4.9 and the section I'm covering today is 5.2. It will make more sense and be a more cohesive run of material if we cover 5.1 and 5.2 in their entirety before introducing 4.9 and 5.3. You'll see what I mean. I promise it will work out better this way. So without further ado, let's get to it. So today, I'm going to introduce the definite integral. Which is section 5.2. A little announcement. We had an awful lot of makeup tests, and I don't like publishing results on a given test before the makeup test is out because they are similar. So your test results, the exam 2 scores, they will be released today, but later in the day. I'm aiming for 10 p.m. because I still actually have, I think, one person who needs to take a makeup, and then we can go ahead and get those out. So let's see. Oh yeah, there's one other thing I need to mention here in announcement territory. The withdrawal deadline for the class is approaching. It's the 24th, which is Wednesday. So if you're having a hard time deciding whether you want to stay in the class or not, the day to make the decision is drawing near. You need to decide by this Wednesday if you want to earn an A through F letter grade in the class. And if you want to do that, you don't have to do anything, just let the day go by, it'll all be good. If you want to withdraw from the class to avoid earning a letter grade, if you would rather get a W for the class than an A through F letter grade, then you'll need to go ahead and withdraw from the class by this Wednesday. The standard advice here is that if you passed both exams 1 and 2, you should stay in the class, you're good to go. If you failed both exams 1 and 2, then the smart move is to withdraw. Don't take the L on your GPA. It's much better to have a W than a D or an F. And then if one went well and the other one didn't, like, you get a 75 or an 80 on exam 1 and then like a 55 or a 60 on exam 2, something like that, or vice versa, then you should probably talk to your advisor, talk to me in office hours, and come up with a plan. There are some things I can do to help here. In certain instances, I can withdraw people late, although not always. And if you feel you're in that limbo space where you're not sure the class is going to go well, but you're not sure the class is going to go badly, then you need to have conversations with the relevant people. Of course, me as the professor is someone you should talk to, but also talking to your advisors and making sure that whatever plan you come up with is something that will fit with your academic goals is important. So just be aware that withdrawal date is coming. It will be 324. If you stay in the class beyond 324, you're getting a letter grade. I think that's all the announcement-y stuff. So without further ado, let's introduce Mr. Integral. The exact signed area, and I'll talk about what I mean by signed area, bounded by f of x and the x-axis is, remember we learned this last time, it's the limit as n goes to infinity of Rn, which is the limit as n goes to infinity, sigma I from 1 to n, f of xi times delta x. This thing has a better name. So the object I'm defining here is the object on the right. That's what the two dots by the equal sign mean. We call this the integral from a to b. That's how that symbol is read. It's the integral from a to b of f of x dx. And before we get into mechanics of this thing, I want to just talk a little bit about the notation. The symbol here, which is called an integral symbol, is a Latin letter S. Right? The Latin alphabet is the alphabet we use in English, right? It's our alphabet. The letter S, it's just like the letter S you see in the word signed, or more importantly, it's the same as the letter S you see in the word sum. So just like this capital sigma here stands for sum, S-U-M, the capital S here also stands for sum, S-U-M. It's just that here we're summing over all the real numbers from A to B. And here we're summing over a discrete index set. I'm sorry, just one second. Okay, no. All right, good. All right, I apologize. I moved recently. There's some lawn care folks working out back. I wasn't expecting that. So this capital S here stands for sum in the same way that this capital sigma here stands for sum. Only instead of having integers like 1, 2, 3, 4, 5 up to n, we're summing all of the y values on the graph over the continuous interval AB. And that's a very confusing thing to do. So I'm going to add up all those y values. And that's why we have this kind of complicated definition. Really, though, the way to interpret this and the way to understand it is as an area. You can think of this as being a height and this as being a very, very little width, infinitely small width times the height of a single point. That's really what we're looking at here. So this whole thing returns the area bounded by f of x and the x-axis. It's equal to the limit of the Riemann sum, which we saw last week gives the exact area. The trick here is this word signed. Bounded by f and the x-axis. We should say here from x equals a to x equals b. That's important. All right. So what do we mean by signed area? I want to talk about that a little bit. And then let's see what we can do with this thing, see what sort of properties it has. So by signed area, we mean that area above the x-axis or above the horizontal axis is measured as positive. And area under the x-axis is measured as negative. That's what the word signed means. So if I was looking at the integral from a to b of a function that is sometimes positive above the x-axis and other times negative below the x-axis on that interval, maybe I'm looking at something like this. Maybe a is here and maybe b is over here. Then I can kind of think about this as having separate regions. Certainly there's some area up here. There is some area down here. And there's some area over here. So if I say that each one of these regions has area, maybe A1 here, maybe A2 here, and maybe A3 here, where this is the graph of f of x, then the integral from a to b of f of x dx would be equal to the areas. But this one is beneath the horizontal x-axis, so it will be measured as negative. So this would be positive a1 minus a2 plus a3. So that's what we mean by the word signed. Areas, of course, are always positive, right? If I ask you how much area is there here, the answer is a2. But if I ask you what does this contribute to the integral, the answer would be negative a2, because that bit of area is beneath the x-axis. Is this making sense? All right, I'm going to give you guys a second to write, fill up my coffee. I apologize, give me just 10 seconds. So the goals for today are to get you comfortable with the integral notation and to show you how to evaluate some integrals geometrically. And we can also talk about some of the properties of the definite integral, but before we get into any of that, I need to talk about when we can do this. Just like we can't differentiate every function in the world, remember like the absolute value function, he can't be differentiated there at that pointy part. He is not differentiable there. There are some similar restrictions for integrals. It turns out that integrability is a much looser thing than differentiability. There are a lot of functions that are not differentiable, but are integrable. So I want to talk about that for just a second. Before I move on from this, are there any questions about this definition or what we mean by signed area? Okay. Just like not all functions are differentiable, meaning have a derivative, not all functions are integrable. Have an integral. There is a really neat connection between differentiable and differentiation and integrable and integration. And we'll talk about that when we get to the fundamental theorem of calculus. Oh, sorry. We'll talk about that when we get to the fundamental theorem of calculus. But before we even approach that, we need to get an idea for what sort of functions we can integrate. In order to have an integral, we need to be able to talk about the area. And there are some functions where it's very challenging to talk about the area. Let me give you the theorem or the fact. So in the same way that differentiability happens a point at a time, right? Like not all functions are differentiable everywhere, but most functions are differentiable somewhere. It depends on what x values you're talking about. The same is true for integrals. It depends on where we're talking about. So we say if f of x has finitely many jump discontinuities, and no infinite discontinuities, on the interval AB, then f of x is integrable on AB. And if you violate either of these things, you have infinitely many jump discontinuities or infinitely many or any infinite discontinuities, then you're not going to be integrable on AB. So for example, I'm not going to prove this. The proof here is fairly complicated. I think there is some discussion of the proof in the textbook, but I don't believe they give a full discussion. If you want to see it here. Yeah, so they talk about here's actually your epsilon definition of Riemann integrable, meaning you can choose a partition such that the Riemann sum gets very, very close to the exact area. And by choosing the partition to be finer and finer, you can make the difference between the two as small as you want. But notice they don't prove this shit because the proof would be extremely complicated. You'll do it in an advanced calculus class if you take that using what are called Darboux sums. But for us here, we're just going to look at some examples and try to understand why the theorem is true. So I could ask, is f of x equal 1 over x squared integrable on the interval -1 to 1? What do you guys think? Does anybody have an idea or an opinion here? Let me help you out. The trick, as is often the case, is to picture the graph. What does the graph of 1 over x squared look like?
I mean, I know that it has an asymptote at x equals 0.
Yeah, good. That's the big deal here. So we've got a vertical asymptote at x equals 0. We approach it like this on both sides. And the graph of the function looks like this. We also have horizontal asymptotes out here, although those are not relevant to what we're talking about right now. But Julio's observation that we have a vertical asymptote at x equals 0, that's the big thing. So like here's -1, here's +1. This is an even function, meaning the graph has y-axis symmetry. And if we ask what the integral from -1 to 1 of this thing is measuring, the answer is, well, it should be measuring the area here. But of course, this area goes up and up and up forever. So forget about the definition for a second. Intuitively, is it an easy or reasonable thing to talk about the area bounded by this function from -1 to 1?
Yeah, no, it doesn't make sense.
No, because this area, you know, this goes all the way up to infinity here, right? If I wanted to really sketch this, it goes off the page. It goes up forever and ever and ever, amen. So no, this function is not integrable. Why? Because it has an infinite discontinuity. Has an infinite, but the subtlety here, infinite discontinuity at x equals 0, which is in the interval -1 to 1. Now, is this function integrable from 1 to 2? Yeah, sure. It doesn't have any infinite discontinuities from 1 to 2. But any interval containing 0 is going to have this problem. So we'd say, moreover, f of x equals 1 over x squared is not integrable on any interval containing 0. So 1 to 2 would be fine. -5 to -4 would be fine. But any interval that has 0 inside of it or has 0 as an endpoint is going to be a problem, because you're going to end up integrating in a way that involves the vertical asymptote. Specifically, we say this function has an infinite discontinuity at x equals 0. Remember when we talked about classifying discontinuities? You've got jump discontinuities, removable discontinuities, and infinite discontinuities. Removable discontinuities, it turns out, we don't even give a fuck about those. The integral does not care about removable discontinuities. Those are fine. But jump discontinuities, you need to have finitely many of them. And infinite discontinuities, you can't have any of them. This function does have an infinite discontinuity on this interval, specifically at 0, so it's not integrable there. Turns out there are ways to get around this using different kinds of integrals. The integral that we define is what's called the Riemann integral, right? We called it a Riemann sum because Riemann came up with it. The integral that you get as a limit of the Riemann sum is called a Riemann integral. So we would say that this function is not Riemann integrable on any interval containing 0. So that's how we can get in trouble with the infinite discontinuity. The other way we can get in trouble is if we have more than finitely many jump discontinuities. All right, so no jump discontinuities, that's fine. 2 jump discontinuities, that's fine. 10 jump discontinuities, that's fine. But if you have infinitely many jump discontinuities, then you can get into trouble. Now, it's hard to come up with a function that has infinitely many discontinuities, but we've seen one before. The Dirichlet function. d of x equals 1 if x is rational, and 0 if x is irrational. This is not integrable on any interval. So no matter what you pick for your interval AB, the Dirichlet function is not going to be Riemann integrable there. Let me remind you what the graph of the Dirichlet function looks like. So it only takes two y values, 1 and 0. At x equals 1, for example, the y value is 1, because 1 is a rational number. At x equals 2, the y value is 1, because 2 is a rational number. At 1/2 and 3/2 and 7/8, at any rational number, this function is equal to 1. And there's a lot more rational numbers in here, right? Like 1/10, 1/5, 1/7, 4/5. There's lots of things up here. And of course, negatives over here. There's lots of rational numbers on this side also. Those will all give us a 1 along this graph. So the graph kind of looks like a faint sprinkling of dust along the horizontal line y equals 1. But here's where we get into trouble. At the square root of 2, this function is equal to 0. Out here at pi, this function is equal to 0. At 3, which is just to the left of pi, the function is equal to 1. But everywhere in here, think pi over 2, pi over 4, pi over 6, any multiple of pi, you're going to get an irrational number. At any multiple of the square root of 2, you're going to get an irrational number. At any multiple of any irrational square root, which is most square roots, you're going to get an irrational number. There's a shitload of irrational numbers. In fact, there's way more irrational numbers than there are rational numbers. This was one of the big discoveries of Georg Cantor at the turn of the 20th century, is that the irrationals way, way, way outnumber the rationals. So much so that if you compare kind of the density of points up here along y equals 1 to the density of points down here along the line y equals 0, this basically is like smoke. This is almost solid. However, between any two real numbers, take your two favorite real numbers, say 0 to 2. Between any two real numbers, there are infinitely many irrationals and infinitely many rationals. So between any two real numbers, there are infinitely many rationals and infinitely many irrationals. And every time the input goes from rational to irrational, this function has a jump, has a discontinuity. So d of x is discontinuous, I should say has a jump discontinuity at every real number. So on any interval AB, d of x has infinitely many jump discontinuities. Therefore, d of x is not integrable. Cannot be integrable on any interval AB. So this second example is fairly exotic, right? It's a weird function. You don't run into these a lot when you're studying calculus because functions like these are kind of strange. They always have to be constructed in some sort of funky way like this, like piecewise definitions over bizarre sets. But they certainly exist. This very much is a function. It's just not a nice function. And it turns out there's lots of functions like these. If you go on to study mathematics in real world context, you'll be surprised how often functions of this nature show up. All right, that's the bad news. Now for the good news. Both of these have workarounds. The workaround for the first issue, something where your function blows up to infinity, is called an improper integral. And you'll learn about these in Calc 2. I'll teach you about those in Calc 2, or whomever you take Calc 2 with. If you go on to Calc 2, we'll teach you about those. They're not Riemann integrals. So the rules that we have in this class, you'll need to be careful in how you apply them there. But there is a way to get around it. It just involves very careful treatment with limits. Basically, you express the improper integral as a limit of proper Riemann integrals, and then you evaluate the proper Riemann integral and take the limit at the end. You'd be surprised. This one works out fairly easily. This one, the workaround is more complicated. If you want to integrate the Dirichlet function or any function like this that has infinitely many discontinuities, you're going to need something called measure theory. And measure theory is not something you're going to run into usually until you're, about a year into graduate school as a math student. Or if you go on to study something like statistics and probability, if you study that very seriously, you might learn some measure theory as an undergrad, it depends. But the workaround for this sort of issue is much harder than the workaround for this sort of issue. The good news is in this class, you're not going to have to fuck with either of those. Right, that you won't have to worry about dealing with either of those situations. You'll just need to know when you're in one of them. So if I ask you on a test, is this function integrable or not? You need to be looking for these two things. Does the function have any infinite discontinuities? Does it have any vertical asymptotes, basically? If it does, then it's if it does, and that vertical asymptote is on this interval, or whatever interval you're being asked about, then that function is not integrable there. The other thing you need to watch out for, does this function have infinitely many discontinuities on that interval? If it does, then it's not integrable. If it doesn't, then it is integrable. And most of the time, the answers to these will be very, very obvious. It's not something we beat on too hard in Calc 1, but it's something you should be aware of. Questions on what we mean by integrable? I hope you see that at its heart, the challenge here is just, is there an easy way to talk about the area? Here, it's very hard to talk about the area because this little bit goes up and up and up forever. So if something is infinitely tall, does it automatically have infinite area? Turns out the answer is no. Turns out the answer is very subtle and depends on some very particular characteristics of the function. It can go either way, but the infinite height is what makes this hard to figure out. Over here, it's that the little bits that are up here at 1 are infinitely thin. So how much area does 1 point contribute? like the point at 2 right here, what's the area under that point? We never draw points as being infinitely thin because you can't draw something that's infinitely thin. But in reality, a point is infinitely thin. So the amount of area that's underneath that one point is 0. Well, what if you take a bunch of little isolated points? The area underneath each of them should be 0. But how many points do you need to have all next to each other before you get a non-zero area? It turns out that, again, is a very complicated question, depending on something to do with what's called topology. To get something that has a measurable area, you need to have a solid piece. And since there's no solid pieces up here, these really are just little points next to each other. They're not right next to each other. There are points that are very, very close to each other, but they're not touching. There is no solid piece up there. It turns out that the answer is there is no area underneath this thing because this thing is nowhere solid. But the concrete answers to those questions require very delicate work in the area of measure theory. So they're not questions we're even going to attempt to answer here. But you should be aware that these are the ways we can get into trouble. Okay, let's play around a little bit with this concept of signed area. So I'm going to draw a graph. Let's do it like this. Ah, shit, that should have been at 2. All right, and put this one down here at 1. Okay. So just so we're clear, this line is at y value 2. I know my art is bad. This line is at y value 1. And this line down here, we're going to say is at y value -2. I want to find a handful of integrals here. I want to find the integral from -3 to -1 of f of x dx. I want to find the integral from -1 to 1 of f of x dx. I want to find the integral from 1 to 3 of f of x dx. And let me find also the integral from -3 to +3 of f of x dx. And I'll say here the height is 2. And the height here is 1. Because I know my picture didn't get that across nicely. And the graph here, of course, is the graph y equals f of x. This is the x-axis. All right. Starting with this first guy. This is read as the integral from -3 to -1 of f of x dx. Remember, that should be the signed area bounded by f of x from -3 to 1. So somebody help me out. How do I find this? Who can make a recommendation here? Who can tell me a little bit what I'm looking for? Yes, I see there's something in chat. Yeah, it certainly has to do with the y value. So this first integral is measuring the area of this region, right? It's not just the y value though. It's the area. I'm sorry, Julio, what was that?
Oh, I was just saying that is we could just find like dx or delta x.
So we don't need to go that far here. Neatly, we can use the geometry of the graph because all the little areas here are rectangles. So it's true that one way to approach this would be to set up the Riemann sum, right? We could set up the Riemann sum using n rectangles and then take a limit as n goes to infinity. That's the hard way though. Because this graph isn't at all curvy, it's nice and flat, we can talk about the exact area without using any complicated Riemann sums. This whole little region here, which
Oh
is
right, yeah.
the area being measured here, is a rectangle, yeah.
Yeah.
So what's the width of this rectangle?
Yeah, 3.
We go from -3 to -1. How much width is there between -3 and -1? Yeah, 2, right? Thomas got it in chat there. The width of this rectangle is 2, and the height of this rectangle is 2. So the area here is 4. It's above the x-axis, so we count it as positive. Is everybody understanding this? I know it's a little bit weird, but this whole region here is just a 2 by 2 rectangle. So its area is 4, 2 times 2. What if I want to integrate from -1 to 1? That means I'm just looking at this piece right here. So first, questions on this. I'll make sure we're 100% comfortable with this. This is the integral from -3 to -1 of f of x dx. So that should be the signed area bounded by the purple curve between -3 and -1. Since my function is constant from -3 to -1, it has a constant height. There's nothing curvy. I don't need to do anything fancy. I can just say, okay, well, that area is the area of this little rectangle here. It's above the x-axis, so it will be measured as positive. The width is 2, the height is 2, so the area is 4. So this integral is 4. Can I get some affirmative consent to move on to the next one? Are we 100% comfortable with why this is 4? I appreciate that. Thank you, thank you. Okay. Seems like we're comfy. I got lots of yeps and thumbs ups. Good. Now from -1 to 1, that's my second integral here. I want to integrate f of x from -1 to 1. That means I'm only interested in the area bounded by this function between -1 and +1 on the x-axis. So I'm looking at this interval here. This is the interval from -1 to 1. The area here is this region. Again, I have a rectangle because again, my function is constant on that interval. So from -1 to +1, this width is again 2, right? Step 1 here, step 1 here, total width is 2. The height of this rectangle is also 2, right? From -2 up to 0, that's a height of 2. So the area here is 2, but the signed area is -2. because this is beneath the x-axis. Remember this picture. The A2 piece, which is beneath the x-axis, gets measured as negative. That's what we mean by signed area, and that's what the integral gives us. So from -1 to 1, my function is the constant function -2. The area here, if we were just measuring the area, would be 4. But since it's beneath the x-axis, we measure this as negative. So this one would be -4. Are we comfy with that? All right, let's look at the integral from 1 to 3. So from 1 to 3, yeah, good. Thank you, Tahara. That is exactly correct. From 1 to 3, I have a rectangle here whose height is 1 and whose width is 2. So the total area here is 2, and it's all above the x-axis. So this guy comes out to 2. Now for the fun question. What's the integral from -3 to 3? Excellent. Yeah, it's the same sort of thing as we saw on that previous page. We've got a positive bit, a negative bit, and a positive bit. So it's going to be plus this, minus this, plus this, which is +4 minus 4 plus 2. And in fact, what you'll see here is that this can be considered as the integral from -3 to -1 plus the integral from -1 to +1 plus the integral from +1 to +3. I'm going to put this is not necessary for the solution of the problem, but I just want you to note that this is equal to the integral from -3 to -1 of f of x dx plus the integral from -1 to +1 of f of x dx plus the integral from +1 to +3 of f of x dx. And you can always split up integrals like that. It's a neat feature of the definite integral that comes very intuitively from the definition as a signed area. Questions on this? Yeah, so we should say here this is of course eventually going to be equal to 2. So the more general thing that this is hinting at is a theorem. It's a property of the definite integral. I'm going to give you the whole thing. And I'll prove it. The proof will be sort of a picture. The first is that if here I'm assuming f is integrable, the integral from a to b of some constant k times f of x dx is equal to k times the integral from a to b of f of x dx. 2, the integral from a to b of a sum of two functions, f of x plus, or a difference, minus g of x dx, is equal to the sum or difference of those integrals, a to b f of x dx plus or minus integral a to b g of x dx. Both of these come from the properties of the sum. Remember when we talked about properties of the summation operator, the sigma, it had these two properties. These were called linearity. Because the sum is linear, the integral is linear, because the integral is a limit of the sum. Here, k has to be a constant. The third one, though, this is fun. The third property that I want to show you is the one that's illustrated above, that if A is less than C is less than B, then the integral from A to B of f of x dx, sorry, one of my other classes' Discord is getting busy now, is equal to the integral from A to C of f of x dx plus the integral from C to B of f of x dx. I'm going to mute those two. Discord really quickly. Sorry for the noise. Here, how do I mute this tab? There it is. Mute, mute. So these are the basic properties of the definite integral. The integral is linear. It works just like the sum. Constants pop out, and you can split up over addition or subtraction. This last one is something else. This is not linearity. And I'd like to illustrate this for you now. So I'm going to give you a quick proof, a little picture proof of the third item. The first two, we'll say we're going to prove the whole theorem. Items 1 and 2 come from linearity of the sum. Come from linearity of capital sigma. The integral a to b of k times f of x dx is by definition equal to the limit as n goes to infinity, sigma I from 1 to n, k times f of xi times delta x. And that k is a constant. It doesn't have any i's in it, so it can come out of the sum. And since it doesn't have any n's in it, it can come out of the limit. And then what you realize is that the object right here is the integral from a to b of plain old f of x dx. So this is the proof of the first item. Very straightforward. Follows immediately from the definition and the linearity of the sum. Right here to right here is where I'm using the property that this constant can pop out of the sum. And then once it pops out of the sum, it can pop out of the limit. Remember, that's another rule we have, that constants pop out of limits, just like they pop out of sums and derivatives. Once you pop the k all the way out, what's left here is the definition of this integral. Item 2. So here's 1. Item 2. The integral from a to b of f of x plus or minus g of x dx is by definition the limit as n goes to infinity, sigma I 1 to n, f of xi plus or minus g of xi all times delta x. And you can probably smell where this is going. The sum splits up over this addition or subtraction. So we get limit n to infinity. I'll write it with a bracket here. Sigma I from 1 to n, f of xi plus or minus of delta x, sorry. Sum I from 1 to n, g of xi delta x. And then you can give the limit to each piece. So here we're using properties of the sum and of the limit. So you get lim n to infinity, sigma I from 1 to n, f of xi times delta x plus or minus lim n to infinity, sum I from 1 to n, g of xi times delta x. And each of those on their own are the integral of f from a to b plus or minus the integral of g from a to b. This is integral a to b f of x dx plus or minus integral a to b g of x dx. I would argue that these two are fairly obvious, that constants can pop out of integrals and that integrals can be split up over addition or subtraction really does follow from the properties of capital sigma. But the third one is much cooler. I'm going to hold here for a second. Anybody who's writing. The third property is best understood geometrically. If A is less than C is less than B, that means C is in the middle of A and B, then let's draw the picture. Maybe here's A, over here is B. And remember, C is assumed to be between them. So this is the graph of f of x. And C is somewhere in here. If I'm looking at all of this area, then the area from A to B, all of that area, is the same. So area A to B under f of x dx is the same as what I get if I look at the area from A to C and add that to the area from C to B. So they're equal. Therefore, the integral from A to B of f of x dx is equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx. Very cool fact. Surprisingly useful. It's kind of obvious as it is from the picture, it's surprisingly useful. So these are the three properties of the definite integral that we want to keep in mind as we are just getting started. And as always, you're not responsible for the proofs, but you are responsible for the statement of and the application of the theorem. So the last thing I would like to do today, we're getting close, is solve a few problems. Right? We've looked at this problem. This is a good one. This is neat. There's a few other sort of things that I want to prepare you to do. First, I'd like to see if I can give you a sum and have you write it as an integral. So let's express lim n to infinity, sigma I from 1 to n, xi cubed plus xi times the sine of xi all times delta x as an integral over the interval, sure, 0 to pi. So we wanted to go back and look at the proof of the third item for a second longer. It's just the picture. There isn't any sort of technical work going on here. So this first area here is the integral. This first piece here is the integral from a to c of f of x dx. The second piece is the integral from c to b of f of x dx. And the whole area is the integral from a to b. So if you add the two little areas, you get the big area. So this is the big area. This is the first little area. And this is the second little area. So if you add the two little areas, the area from here to here and the area from here to here, you get the big area. The way we use this is if you're given something like this, right, and it's easier to compute the two little areas on their own, then you compute the two little areas as their own things, and then you add them up. It's especially useful for piecewise functions. So the three properties were just these. These are the bits that you really need to remember. So constants pop out. Constant multiples pop out. You can split up over addition or subtraction. And if you have some number in the middle between a and b, then the integral from a to b is the integral from a up to that number in the middle, plus the integral from that number in the middle up to b. Okay. Use that picture one more time if you need to make sure that's clear. And now if we're good, I am going to return to the little problem we were just starting. If you need a screen cap, go ahead and take one. And here we go. All right. So this problem asks me to express this limit of a Riemann sum as an integral over the interval 0 to pi. And the trick here is just to match up the pieces. remember your Riemann sum, there's a delta x at the end. Your Riemann sum is lim n to infinity sum I from 1 to n f of xi times delta x. So this has to be f of xi. So the question is, what's my function? If f of xi is xi cubed plus xi times sine of xi, what's the function that I've plugged xi into there? What is the function f of x? Well, I mean, it's what you would have if there weren't i's here, if they were just x's. It's x plus x sine x. And then all the other pieces match up. The delta x matches up with the dx in the integral. The sigma, the limit, and the sigma together turn into the integral symbol. So this is equal to the integral of x cubed plus x sine x dx. So the delta x kind of becomes a dx, f of xi becomes good old f of x, and all of this stuff becomes the integral. And they were kind enough to tell us that we're working from 0 to pi. There are problems of this nature where they don't tell us that, but in those problems, they would have to give us some clues. Like instead of writing delta x, they'd have to tell us what delta x actually is. Instead of writing xi, they'd have to use what xi actually is. So this is our answer here. And these aren't too hard because you don't have to do any computation. You just have to kind of match up the pieces. But there are other problems. Like say I want to evaluate the integral from, let me go with -2 to 2 of x plus 1 dx. And I'm going to add on here geometrically. So one of the options is to build a Riemann sum for this thing. You could do that. You could, and you have all the necessary summation formulas. We had problems like this last week. Only instead of saying evaluate this integral, I said find the exact area under the curve. There will be problems like that on this week's homework set, where you begin by saying what delta x is, and then finding what your xi's are, and then writing the limit of the sum, and then computing the sum, and then taking the limit. But this is not one of those. They say to do it geometrically. So we should look at the graph and try to apply some rules from geometry. So I'm going to call that 1, we're going to call that 2. Here would be -1, and here would be -2. The graph here is of f of x equals x plus 1, because that's the function I'm integrating. And the value of the integral should be the signed area bounded by this function. So what you notice is that the region in question is made up of pieces whose areas we can find using formulas from geometry. Namely, it's two triangles. So the little triangle has area equal to 1/2 base times height. The base of the little triangle here is 1, right? It goes from -2 up to -1. That's a length of 1. And the height of the little triangle, to find that, we need to know what this point is. Well, what's this point on the graph here? It's -2 comma what? Somebody help me out. I'm on the graph, f of x equals x plus 1.
-1.
Yeah, good, -1. So what's the height of this triangle?
Be -1 or 1.
Yeah, strictly speaking, the height is a length. So the height is 1. So this would be 1/2 times 1 times 1, which is 1/2. That's the area. Now we're going to talk about signed area eventually, but to start with, I just want to identify the actual area, and then we'll worry about what's positive and what's negative. But those of you who are thinking that this should be measured as negative are correct. Let's play the same game over here. I've got this triangle. So the big triangle area it's also 1/2 base times height. His base goes from -1 all the way out to 2. So what is this length?
3.
Good. And to find the height up here, we need to know what is the y value on that graph. So this is 2 comma what? Good, 3 again. All right, because if you plug in 2 here, you get 2 plus 1 is 3. So this is 1/2 times 3 times 3, which is 9/2. So then the integral from -2 to 2 of x plus 1 dx is this guy, but with a negative because he's beneath the x-axis, plus this guy, who's positive because he's above the x-axis. And if you add -1/2 to 9/2, you get 8/2, which most people would just call 4. So the integral here is 4. Questions about this bad boy? Okay, I've got one more of these where we're going to use geometry. I'll ask you to be patient with me. I know we're going a little bit over, but I want to close strong here. Same thing. Evaluate the integral from 0 to 1 of the square root of 1 minus x squared dx geometrically. Again, we begin with the graph. So what does the graph of y equals the square root of 1 minus x squared look like? This is a fairly complicated looking function, right? Does anybody know? Maybe it's a little hard to see right now. So let me square both sides. On the right-hand side here, this square and this square root cancel. So we get y squared equals 1 minus x squared. And then if you add x squared to both sides, you get x squared plus y squared equals 1. Does anybody know what that is the equation of?
This is a circle, right?
Yeah, it is. This is a circle. What kind of circle? Good. Circle of radius 1. Centered where? At 0, 0. Right? So remember the equation of a circle centered at a comma b with radius r has equation x minus a squared plus y minus b squared equals r squared. So here a is 0, b is 0, and r is 1. So do I have the whole circle here?
It has a restriction as domain.
There is,
For-
yeah, that's okay. But I'm more interested in something to do with the range. Is this equivalent to this? Notice one of those arrows only goes one way. Yeah, I didn't draw this arrow as pointing both ways. Why? What happens? Imagine you just take this line and you solve it for y. Good, it's to do with the radical, specifically what? If I take square roots on both sides here, what do I get? I would get plus and minus this thing. So the graph of y equals square root 1 minus x squared sorry for my bad art here, is really just the upper semicircle. The whole thing, x squared plus y squared equals 1, is the whole unit circle. But because we have the positive square root only, we just get the upper semicircle. So I can show you in Desmos really quickly. Here we go. So here's the graph of y equals square root 1 minus x squared. Here's the graph of x squared plus y squared equals 1, right? The whole circle versus just the semicircle. If you solve this for y, you'll get plus and minus. So the negative square root gives you the green lower semicircle. The positive square root gives you the red upper semicircle. Here we have just the positive square root, so it's just the upper semicircle. Now we're ready to solve the problem. I want the integral from 0 over here up to 1 over here. So I'm looking just for the area of this quarter of the unit circle. Weird hair there. Therefore, the integral from 0 to 1 of the square root of 1 minus x squared dx is equal to 1/4 the area of the circle. Now this is a circle with radius 1, so this is pi times 1 squared. 1 squared is 1, so this is pi over 4. So the integral from 0 to 1 of the square root of 1 minus x squared is pi over 4. Now something cool I'm going to share with you just on the way out. This is it, we're done. I'm going to teach you lots of methods in this class for evaluating integrals. I'm going to teach you like 3 or 4 methods for evaluating integrals. But this one can only be done this way. In Calc 2, I'll teach you a way to evaluate this directly using the fundamental theorem of calculus and something called trig sub. It involves substituting a trig function in for x. It's somewhat complicated. But the fact that we can solve this integral geometrically just by thinking of it in terms of an area is a really powerful thing. And it's just one little window into how powerful choosing to think of things geometrically can be. If I gave this problem to a Calc 2 student, they would dive in and try to do trig sub, but they don't need to. All they had to do is realize it's a circle and call it a day. So be mindful of the interplay between the geometry and the calculus. It can be extremely useful and very, very helpful for saving time. That is it from me for today. On Wednesday, Katie is going to talk to us about antiderivatives. And then on Friday, I'm going to show you how antiderivatives connect to this area problem. And that's going to be the rest of our week. So I hope you guys enjoyed today's lecture. I'm going to post some homework for you to start working on here in the next 3 minutes. And then I would expect you guys to take a look at a few of those homework problems before Katie's lecture on Wednesday. That way you'll feel a little bit more comfortable with the definite integral, and you'll be able to understand the connection between Katie's antiderivative lecture and my fundamental theorem of calculus lecture on Friday. Tahara asks why we multiplied the area of the circle by 1/4. Because we only wanted the integral from 0 to 1, and my function is just the upper semicircle. So in other words, that integral is measuring just the shaded area here, right? This thing is not a part of my graph, and I'm not going from -1 to 1, I'm just going from 0 to 1. So I really just, all the integral is asking therefore is to find the area bounded by this part of the curve. And that is this shaded region in here. And because of the way the geometry works out, this shaded region is exactly 1/4 the area of the circle. Cool. All right. Hope you guys have a lovely rest of your day. Please do watch out for that homework. It will be opening up in a little bit, and then I'll have your exam scores out this evening. That is it from me. I hope you have a wonderful day, and I will see you either in office hours or next time.